talk is going to be fairly elementary, and we're just going to introduce orders and do some easy to medium problems. Okay, so let's just define order. Um, and let's just start with an example. Um well, I mean, if you've seen something like, let's just start with 3 and keep multiplying 3. And let's look at the unit digit. So what would the pattern of the unit digit be?
3971.
Okay, right? Because 9 times 3 is 27, which is 7 mod 10. So, okay. So we look at 3, 3 square, 3 cube, 3 to the 4, 3 to the 5, etc. And we want to focus on the unit digit. The unit digit is 3, 9, 7, 1, 3, and the pattern repeats, right? Yeah. So mod 10, it has this period 4, right? And in general, we, well, given any A and B co-prime to each other, I will use this notation for, okay, let me actually write GCD because later on if we have tuples, it's confusing. Let's say we have GCD AB equal to 1, and let's just say, okay, let's say B is greater than 1 just for comfort. Yeah. Then if we look at this sequence mod B, then it will repeat. Why does it repeat?
Because due to being relatively prime, there needs to be some place like phi of b, where the remainder will be 1 only.
Can you give me a more elementary proof of repetition without using phi of B? Sorry, who answered that question?
It was me.
Yeah, can do you have a more elementary proof in mind?
Not
Like,
really. Only
Should
one
I tell?
mention here.
okay,
Also, isn't it because like mod B, there are only like a limited number of possible remainders, and after one point they will after like one that connects to another, then the cycle has to repeat over again.
yes, exactly. Yeah. So it basically we're exploiting pigeonhole principle, right? So we're saying that look at these numbers, a square, a cube, up to a to the b plus 1. These are b plus 1 different items, elements, whatever. And mod b, there are only b possibilities. So then some two of them must match. So let's just say a to the I and a to the j match. So then it becomes periodic from this point onwards. But I want to prove that it's periodic from the starting. So what do I do? So I know that there is a to the I congruent to a to the j mod b by pigeonhole principle, where 1 less than equal to I less than j. In fact, I also know less than equal to b plus 1. But then how do I prove that this sequence is actually periodic from the very start?
Since P and A are co-prime, you can just divide by A to the
Maybe
power I.
just see that a to the I minus g will j will have one mod. Will be one mod b.
Yes. So since, well, since a and b are co-prime, we can sort of just divide and get 1 congruent to a to the j minus I mod b. And so this means uh, we actually repeat with period j minus I, because a to the j minus I plus 1 would be a mod b. Alternatively, if you want to start from a to the 0, which is 1, then a to the 0 and a to the j minus I are equivalent. And so we have a period which is j minus I. Yeah. Okay, great. So So the period can be smaller, but doesn't matter. We just wanted this. And the point is, okay, so the definition is the uh, given uh, a, b integers and b not equal to 0 and GCD AB equal to 1, the order of A modulo B is the smallest natural number. Uh, in this talk, by natural number, I mean 1, 2, 3, 4 onwards. So I don't consider 0 a natural number. It's the smallest natural number h such that a to the h is congruent to 1 mod b. Note that we've already shown existence, so this definition makes sense. You need existence for this definition to actually make sense, right? Okay, great. Um, and what are sort of the properties of order? Um, like, yeah. So, what if you've seen order before? What do you know about order?
Orders are multiple of like phi of b.
Factor, you mean?
It should be multiple.
No, I mean,
They can be the factors.
I'm sorry. Could you say that once more?
Like they can be the factors of phi of b.
Yeah, in fact, h is always a factor of phi of b. It's not a multiple of phi of b.
But this works for only a greater than 1.
Why is that? If a is equal to 1, then h is 1, right?
Then the phi of 1 will be undefined.
Yeah, but we're looking at phi of b, not phi of a.
If A is equal to 1, then h can be anything, right?
Uh, I mean, but it's the smallest. Yeah, okay.
We
Let's
should
just
put a
for our
restriction
comfort.
on them, right?
Yeah, let's just take not equal. Let's just take b more than 1. Yeah, that's the easiest thing. Yeah, okay. So property 1.
So what exactly is an order?
So it's the smallest h for which you start repeating, right?
Oh,
So
okay.
yeah, it's the smallest natural h such that a to the h is 1 mod b. So, for example, I mean, the order of 2 mod 7 is 3 because 2 cube is 1 mod 7, but nothing smaller is 1 mod 7. Yeah. So, okay, yeah, I should have written the notation first. We denote this order as order uh, of A with respect to B. Yeah. Okay, great. Um, yeah. So property 1. So suppose, okay, suppose there is some natural number D such that A to the D is 1 mod B. Then what can we say about H and D?
D is a multiple of h
D is a, yes,
Why?
multiple.
because the cycles are like they have a definite length.
Can I tell why?
No, no. Let me actually say.
Okay, okay.
No, isn't it because like every h times like the cycle repeats, so then D is like a multiple of it?
Well, but maybe it also repeats every D steps and also repeats every H steps. Like, why is that
Oh.
a why is that like you know like is there a contradiction or
Can I
can
give a contradiction?
wait? I mean you know it, so I just want someone who doesn't know it to think about it.
Okay, okay.
Uh,
Wait, I,
So
I don't
yeah.
know.
Um. Okay. So Um, so suppose a to the d is 1 mod b and to the h is also 1 mod b. Then what exactly is the problem? Like, okay, so let's take an example, right? So suppose suppose 4 is the order, yeah, and suppose I'm also able to get that 6 satisfies this, and I said that 4 is the order. Where is the contradiction? Can you derive a contradiction from this? Can you get a smaller number than 4 such that a to the that number is 1 mod b?
Yeah, also 2, right?
Yes, exactly. The point is that from this we will deduce that a square is 1 mod b. But that's a contradiction, right? Because I said that 4 is the order. So how can a to the something smaller than 4 be 1 mod b? Because by definition of order is the smallest natural number for which a to the h is 1 mod b. Right? So this cannot happen. Do you see something similar that happens if d is not a multiple of h? So let's take something else, right? So let's say a to the 4 is 1 mod b, and somehow I'm able to deduce that a to the 15 is 1 mod b. Is there an audio issue on everyone's side? Am I not loud
You are
enough?
audible.
There is not an issue, but the voice is very low.
Okay, okay. Uh, yeah. So the problem is that it's like 4 a.m. So my roommate's sleeping. I can't be
Okay,
too
no
loud.
problem. You can
So it's
set
fine,
the
I
time.
think. Maybe your like device volume is too low. It's fine for me.
Uh,
Not you, like the
oh,
people who cannot hear it loudly.
yeah, I'm not sure. Maybe not everyone has headphones or earphones on. Yeah, so where is the contradiction with this? Suppose 4 is the order. So, yeah,
Or shall I?
no,
Okay.
maybe it's someone else. I encourage everyone to try it actually. Uh, and do speak up if you're comfortable. It's always good to have interactions. Even if you're wrong, it's fine. Doesn't matter. Okay, so can you deduce a to the 11 mod b?
That's 1 because 15, a to the power 15 by a to the power 4 is like
Yes.
a to the power 11.
What about a to the 7
That's also 1.
and a to the 3?
Oh, right, that's also 1. So 4 can't
Nothing.
be the order.
Exactly. So the point is that if if it is not a factor of d, then note that a to the um, uh, d mod h, I guess. I mean, what I mean to say is the remainder when d is divided by h is congruent to 1 mod b. Call this r, right? But then this r is strictly between 0 and h, which is a contradiction, right? Because now a to the r is 1 mod b and r is a natural number less than h. Yeah. So this means h is actually a factor of d. Yeah. Okay, great. Um, so in particular, so I'm assuming people are comfortable with the phi function. Just let me know if you don't know what the phi function is. It's the Euler-Toschen function.
It's the number of open numbers less than or less than equal to n.
Uh, it's less than equal to, right?
Wait, it's all the stuff that is like co-prime to it, but lesser than the number, right?
Less than equal, like phi of 1
Yeah,
is
but
1, right?
less
By
than equal to
definition.
won't matter because a number
For 1
isn't
it
co-prime
matters.
to it.
For 1 it matters, right?
Oh, right.
And by definition, I think, yeah, phi of 1 is 1 and not 0. Yeah. Yeah, so then I think someone who pointed out that for b equal to 1, it's a problem. I don't think it's a problem then, right? Because phi of 1 is 1.
Yes, but my definition of phi was different.
Oh, yeah, I mean, phi of 1 is 1, so it's fine. In fact, let's just take positive. That's just easiest. Besides, I mean, you don't have to be exactly technical with these definitions. It's fine. I mean, nobody's going to use this theorem for b equal to 1 or do all of this for b equal to 1. Okay. Yeah, so we have h divides d. And in particular, so I don't think anyone said that they don't know what the phi function is. So I'm going to write that this means h divides the torsion function of b. Yeah. Okay, great.
But why does it? Why is the torsion function of B?
Well, because note that by Euler's theorem, a to the phi of b is 1 mod b, right? Uh,
Yeah.
Euler, a to the phi of b is congruent to 1 mod b. And so this
Oh,
immediately
right.
means
Yeah.
that h actually divides phi of b. And actually, it's kind of a misconception that I think I've seen too many scripts that do this, but people just assume that the order is equal to phi of b, which is not true. Yeah, so just be careful there. Yeah, in fact, sometimes there are numbers for which there is no other number whose order is exactly phi of b. For example, take 12. Yeah, so let's take b equal to 12. Then what are the numbers co-prime to it? I mean, mod 12 is what it matters, right? So 1, 5, 7, and 11. And note that all of their orders are actually 2 because 1 square, 5 square, 7 square, and 11 square are all 1 mod 12. And so, in fact, there is no A for which phi of 12 is the order of A mod 12. So, yeah. Okay, great. All right. Uh, let's.
Aren't all numbers like completely divisible by one? Why does one also like come under the thing?
Oh, sorry. The order of 1 is 1, by the way. I don't know why I wrote that. 1 to the 1 is 1 mod 12. Yeah, sorry. You were saying?
No, I asked like all numbers are divisible by one. Right? Why is one counted in the torsion function?
It's just definition.
It's like co-prime number, no? So 1 comma 12 is 1 only.
Like we take the GCD is always one.
Oh, right. Yeah.
Yeah. Okay, I mean, phi of n is defined as the cardinality of the set of all naturals M such that M is a natural, M is less than or equal to n, and GCD of Mn is 1. Also, I mean, you can define things where you don't take 1 or you don't take n. The point is that this torsion function has really good properties. Like it has this property that if M and n are co-prime, then phi of Mn is phi of m times phi of n, for example. It has these nice properties. Right? So, I mean, if you modify the definition, then these might not hold true. So, yeah, phi is very well behaved. And in fact, I mean, I guess if we get into number theoretic functions some other day, then we can talk more about why phi is so important. It's like the inverse of some other nice function, number theoretic function, whatever. So, okay, so suppose, okay, now instead of b, I'll use n everywhere because that's the standard notation. So, okay, so now a and n are co-prime everywhere. I won't mention this again and again. Yeah. So suppose a to the h is 1 mod n, h is the order. What is the order of a to the k mod n, where k is some integer? So the answer should be in terms of h and k only. Uh,
K
yeah.
mod h.
Hmm. Um. K mod h. Well, I mean that's not true, right? I mean, if k is 1, then you're saying that the order is 1.
Oh wait, oops, no.
Yeah. So just think about when a
Or
to
we could
yeah.
say a to the power k mod h.
Uh, why is that so?
Because k you have to like subtract like okay, oh never mind.
Can I tell?
Uh, yeah, sure. Just the answer.
LCM of H and K.
Uh, that's not true because if k equal to h, the answer should be 1.
I'm asking about LCM. I'm saying LCM.
Yeah, but LCM of h and h is not 1. Like for k equal to h, the answer should be 1, right? But you're saying that the answer is LCM of k comma h. That's not
I'm
consistent.
assuming that K is greater than H.
Doesn't matter. I mean, for k, okay, so take k equal to 2h. Even then, the answer should be 1.
Okay.
Yeah. I mean, a to the 2h is itself 1. So then the order of a to the 2h is exactly 1. It cannot be LCM of k comma h, right? I mean, the order will always be less than h because a to the k to the h is definitely 1 mod n. So the answer can never exceed h.
So it's like if you take k to be let's say 2, so then it's a square and you need and then one can come in h by 2 steps roughly. No?
I'm sorry, can you say that once more?
So like if let's say k is 2, so you have a square mod n, you need to find the order of that. So we can
Yes.
achieve like a to the power 2 to the power t is basically 1. So a to the power 2t is congruent to 1 mod n, where t is the order of a square.
No, but if you raise this to something that will just multiply with it, it'll become 2k, not 2 to the k. I mean,
Yeah, I meant
this,
2k only.
this,
I meant 2k only.
but where does 2 to the t come in the picture then?
A to the power 2 whole to the power t, I said. That t is the order of a square.
Ah, yes. Okay.
Yeah. So then a to the power 2t is congruent to 1 mod n. So 2t, so a to the power 2t is congruent to h, basically. So t is
You
roughly
mean
h by 2.
2t is congruent to, yeah, I mean, okay, but what happens if what happens
It
if
is
h is odd or something? Then what do you do? Like if the order of a is 3, then the order of a square will also be 3, right? So for example, if the order of a is 3, that is a cube is 1, and the order of a square will also be 3, right? Because
yeah.
a4 is equal to a, and then a6 is actually 1, and so the order of a square is also 3, so it's not roughly 3 by 2.
So basically, if k divides h, then the order is h by k. Otherwise, it's h only.
Not true.
Oh,
There is,
if it's co-prime, then it's h only. If k comma h is 1, then it's h.
yes.
And if
Okay.
oh, is it h by GCD h comma k?
Yes. Okay, so let's see why. So we just want to be able to characterize natural numbers t such that a to the k to the t is 1 mod n, right? Well, since we're looking at order, this is the equation you should look at, right? You should look at the definition and then go into this. And we're trying to find the smallest such t, right? But then note that this is equivalent to a to the kt is 1 mod n. And what is this equivalent to? We just said something about order. So a to the something is 1 mod n, then
H divides KT.
yes. In fact, the converse is also true, right? Because, I mean, I hope you see why the converse is true. Like if a to the h is 1 mod n, then a to the any multiple of h is also 1 mod n, right? Okay. And then what do you say from this? Okay, so now suppose the GCD of h and k is g. Yeah. Then I can divide g. Okay, then I can write h is equal to gh prime, k equal to gk prime, where h prime and k prime are co-prime, right? This sort of, by the way, if you've never seen this sort of an argument before, this is very common in equations, very common technique. It's something that you should note actually and try to apply to problems. Yeah. Okay, and so this is the same as saying gh prime divides gk prime t. And so I can cut g. But now since h prime and k prime are co-prime, this is just equivalent to saying h prime is a factor of t. And so then what is the smallest t that works? The smallest t that works is h prime, right? Which is just h upon g. And so this is the order. Is it clear?
Yeah.
Yes.
Yeah.
Sorry,
Okay.
can you give example?
Yes, I can give an example. Yes, sure. So let me just construct a nice example. Okay. Let's look at the order of 3 mod 7, right? So we're looking at mod 7. 3 square is 2 mod 7. 3 cube is 6 mod 7. Just multiplying 3. Yeah. 3 4 is 18. 6 into 3 is 18, which is 4 mod 7. 3 to the 5 is 12, which is 5 mod 7. And then 3 to the 6 is 1 mod 7. Right? So the order is 3. So order of 3 mod 7 is 6. Yeah. So what would the order of 3 square be? So so we have this formula, by the way, which we can directly apply, which is 3, but we can also think of it logically. Yeah. So logically, the point is that if I'm looking at 3 square, then if I square it, I get here. And if I cube 3 square, I get here. So the order is just 3. Yeah. Similarly, the order of 3 to the 4 is, this is a little more non-trivial. I mean, if since 2 is a factor of 6, it's sort of obvious to see that we'll just divide 2, right? But here this is also 3. We can view this in a similar manner. So we start with 3 to the 4. If you square it, you get to 3 to the 8. But 3 to the 8 is the same as 3 square, right? So, okay. So maybe it's easier if I write this in a circle. 3 square, 3 cube, 3 to the 4, 3 to the 5, 3 to the 6, which is 1, and then back to 3. Yeah. So the point is that if I keep multiplying 3 to the 4, it's like I'm taking like 4 steps on this cycle, right? So I'm starting with sort of 3 to the 0, which is 1, and then I've taken 4 steps at a time and gone to 3 to the 4. Then once I multiply 3 to the 4 again, I take 4 steps on on the cycle and get here. And then the next time I multiply 3 to the 4, I move 4 steps and get to 3 to the 6, which is just 1. And so the order is 3. Yeah, and just another example would be the order of 3 to the 9 is 6 upon GCD 3, 9, 6, which is 2. Which is like 3 to the 9 is like taking 9 steps in one go. And so how many steps must you take to end up here if you started from here? Like, that's just 2, because 9 times 2 is 18, which is 0.6. Yeah. Is it clear? Just to make sure. Okay.
Yeah.
Great.
Yeah.
Yeah. Awesome. Okay. Let's look at yeah. Okay. Yeah. Okay. Yeah. Let me define what a primitive root is now. There will be some definitions in the beginning, but then we can slowly get to problems. Yeah. Primitive root. Let a n have GCD 1, n is greater than 0, a is an integer, n is an integer. Just standard stuff. Yeah. A is said to be. Okay, by the way, I should introduce the notion of a primitive root. So let's, yeah, before definition, I should actually just give you an example. So notice that mod 7, we just looked at 3 right now, right? So, okay, so what are the numbers that are co-prime to 7? The 1, 2, 3, 4, 5, 6, right? And if we start from 2 and keep multiplying 2, 2 square is 4, and 4 into 2 is 8, which is 1, and then 1 times 2 is 2. And so if we start with 2, we don't cover everything, right? I mean, we never get to 3, 5, or 6. And in fact, the order of 2, mod 7 is 3. But if we started from 3, then notice in the previous example, we got to every number. 4 times 3 is 5. 5 times 3 is 15 is 1. Yeah, and so it hit everything. Yeah. 3 is 6. And so this sort of hits everything. This doesn't hit everything. This 1 can obviously not hit everything. It just comes back to itself. So 1 is just like this. 4 doesn't hit everything. The cycle of 4 is somewhat similar
It's
to
just
this.
4 to 1.
Yes, exactly. Does 5 hit everything?
No, it's just 5, 3, 1.
Uh, well, 5 square is 4 mod 7, right?
Yes.
Oh, wait, yeah, it's
5 hits everything, I think. Yeah, it does.
Is this cycle right, by the way? 3, 2, 6, 4, 5, 1. Yeah.
For 5, it's 5, 4, 6, 2, 3, 1, just the reverse of this.
Yes, exactly. Yeah, because 5 the inverse of 3, so it has to be. Yeah, 5 actually hits
Yes.
everything. What about 6?
It doesn't.
Yeah, 6
It's
square is
1.
just 1. Yeah,
It doesn't.
it's just 6 and 1.
yes. So just for 4, 4 is this. Yeah, and 5 is this.
Can we somehow show that the like cycle of an inverse is just like the opposite of that cycle?
Yeah, I mean, uh, I mean, a to the minus k is the same as a to the h minus k, right?
Oh,
Odd.
yes.
Yeah, so that's just direct. Okay, so and this doesn't hit everything. Okay, so these numbers that hit everything, these are called generators or primitive roots. Yeah, let's just take one more
How do we
example.
define it rigorously?
Yeah, I'll define it. Let me just take one more example.
So
For now,
primitive
it's
roots
just,
basically like visit all the mod, everything other than 7. It's like whatever.
yes, everything co-prime to the mod. So let's just take one
Like the
more
order
example
should
to
be
be
n-1 then.
not n-1 because in this case it was prime. But if we take something other than primes, then we may
Like
not have
phi
any.
of n should work here.
Yes,
I
yeah,
totally misinterpreted n. Sorry.
yeah. Okay, yeah, that's fine. So let's just take a different example. Let's just take something silly like 4, right? There's just 1 and 3. 1 obviously doesn't hit everything. 1 is just 1. But then 3 hits everything here, right? 3, 1. We just need to hit everything in this list. We cannot go outside the list because if we start with a number co-prime to 4 and we keep multiplying to itself, we'd always remain co-prime. So we can never hope to hit 2 starting from 3. Yeah, so this is good. So this is a primitive root. Primitive root. Yeah, so just let me define primitive root.
It
So,
doesn't hit everything, right? So how is it a primitive root?
3 hits everything in this list, right?
Oh, the co-prime list basically.
Yes, this list. Yes, the co-prime list. Yes. So
Is this a 5 or 4? 1 or 3?
yes, it's exactly the
Okay.
list of numbers co-prime to 4. Yes.
Okay, the number that hits all the 5 of n is called primitive.
Yes, exactly. That's how I'm going to define it. Sorry, n more than 0. Yeah, okay. Let's just take a not equal to 0 and more than 0. Okay. A is called a generator or a primitive root. I use generator usually. Most books use primitive root, but I just like the word generator. It sounds fancy. Called a generator mod n if um, the order of a mod n is actually phi of n. And it's exactly equivalent to hitting everything, right? Because this list of numbers that are co-prime to n are exactly phi of n in number. And so if you want to hit everything, it's exactly the same as saying that your order is phi of n. Yeah. Is that
Yes,
clear?
makes sense. Yes.
Yeah.
Yeah.
Okay.
Yeah.
Okay. Great. So just one more example. Uh, find a generator. Might just use gen mod 12. Maybe for this purpose, primitive root is easier to write. Just pr. Yeah. Find a primitive root mod 12.
Wait, the only co-prime numbers are 1, 5, 7, and 11, right?
Yes.
Yeah, I get a no.
Sorry, what?
None of them work.
Yeah, you're right. Yeah.
Wait, how is that possible?
Yeah. Well, yeah.
Yes, because 1 squared and 3 squared and 5 squared and 7 squared are one mod.
Yes, exactly. There is none. So, which means that there are natural numbers n for which there are no primitive roots. Uh, can you find another n with no primitive roots?
I think 5.
Well, 5 has a primitive root. Well, 2 is a primitive root, right? 2, 4, 3, 1.
Ah.
It hit. Even 3 is a primitive root. Yeah. It's just 2 inverse. Yeah. What's the smallest? Actually, I should ask them. Smallest n with no primitive root?
8 also doesn't have.
Good. Yes, 8. In fact, you can reduce it directly because maybe if you know that if a is odd, if x is an odd number, then x square minus 1 is a multiple of 8. I think this is in a lot of math. Yeah. So, which means that 1, 3, 5, 7 all have their squares congruent to 1 mod 8. So none of them have order 4, has order 4, which is 5 of 8. Yeah. So 8 is the smallest.
So 8 is the smallest such number, right?
Yes. All of them, all the numbers smaller than it. Yeah.
So is there any special name for that number?
uh, for numbers that have primitive roots.
No, has no primitive root.
Yeah, I mean, it's the equivalent. Yeah. In fact, we will state a theorem characterizing exactly which natural numbers have primitive roots. In fact, most natural numbers do not have primitive roots. So, yeah,
Also,
okay.
6 also doesn't have a primitive.
It does, right? 5 is a primitive root. Only
5 square
co-prime
is
numbers.
congruent to 1.
Yeah, but 1 and 5 are the only numbers co-prime to 6.
Oh, I was taking 3 as co-primers.
Then such a number has order, like for any a which is co-prime to that number, it will have an order less than 5 of n because it makes sense for the theorem.
Sorry, could you say that once more?
The order of that number with the respect to the other number which has no primitive root will have to be shorter than 5 of that n.
Yes. Yeah, for no primitive root. For no primitive roots for every a co-prime to n, the order of a should be less than 5n. Yes. Okay. So there's a question about benefits of having or not having a primitive root. The point is that if you have a primitive root, then it's often easy to sort of to generate the entire set. Yes, just using one number, and then characterizing things becomes easier. So I guess once, if we start to look at problems related to this, I think it'll become easier. Yeah. So uh, okay. uh,
Also, why are they called primitive roots and not advanced roots?
well, I mean, I guess primitive in the sense that they're sort of the they sort of generate everything else. So they're like the ancestor to creating every
Ah,
other number or something. That's the best guess I have. I don't know what the etymology is. Even generator makes sense, right? Generator definitely makes sense. So because it generates everything else. Okay, great. Uh, yeah. Here's another question. It's just take your time to answer. Yeah. So okay. Suppose n has a primitive root. You know this, yeah? N has a primitive root. How many primitive roots does n have? So, well, exactly how many?
it should be an even number
Why so?
because inverse.
Well,
Yes,
the
it
inverse
has
of a
got to
number.
be some even number.
Well, the inverse of a number could be itself, right?
Only if it's 1 or n minus 1.
Uh, why?
Oh, it should. Oh, okay. It can be quadratic residue also, right?
I mean, 3 square is 1 mod 8, but 3 is not 1 or 7 mod 8. Okay. Yeah. Okay. This is somewhat more challenging than the previous problems. As far as we saw the examples, I think one, well, I mean, for 7, we saw that 3 and 5 both work.
It always has, if there's one, then there'll definitely be one more because of the inverse.
Well, 4 only
How do
has
we
3.
notate this number of primitive roots function?
I don't think there's a notation for the number of primitive roots because you know the
Okay, then.
exact formula. So I don't think. I mean, you can call it whatever. Yeah, but I don't think there's a notation for it. Yeah, sorry. Yes, you're saying if there's one, there's always one more. It's not true for 4. It's true for most numbers, probably. Yeah, it's true for large enough n. Yes. In fact, the formula will make it clear why. So one hint is that it's related to a problem that we've done before. Let me just get you started with the problem. So suppose this primitive root is a. Yeah. Then you know that a square, a cube, all the way up to a to the phi of n minus 1, and then 1 itself. This is the exact set of natural integers co-prime to n modulo n. And so I only need to find from this list how many more of them are primitive. So, okay, so the point is given an a to the
Can
k,
I guess? Can I tell?
1 minute.
This k has to be not a like a factor of phi of n.
True. But we've already seen what the order of a to the k is. I mean, we saw this before, right?
Yes.
Yeah.
So that
So, yeah,
h by phi of n by GCD of phi of n and k has to be like phi of n itself. Like then GCD of that k and phi of n has to be 1,
so how many such
implying
k
that k
exist?
is co-prime
Yeah, so
to phi of
2.
n.
Yeah, so how many such k exist? Co-prime to
Phi
phi
of
of
phi
n?
of n.
Yeah,
Yes.
exactly. Yeah, great. So let's just give others a little more time to think. So yeah, when can you say, when is a to the k also a primitive root? That is, yeah, it's fine. I mean, we're not done with the proof yet. I'm still waiting for people to try. So okay. So a simpler question is, for what k? Okay, so okay. What is the order of a to the k? So remember that we've seen this before. So you can go back to it or you can rethink the proof of it.
It's order of A divided by GCD of
Yeah.
A comma 1.
Yeah. So let me just go back to that problem. Here is where we saw it, right? We saw that if the order of A is h, then the order of k, a to the k, is h upon GCD h comma k. Yeah. So, okay. So a to the phi of n is 1 mod n. So here h, which is the order, is phi of n. And so what would the order of a to the k be? So just directly by the formula, it's going to be h, which is phi of n, divided by GCD of h, which is phi of n, and k. Yeah.
But this will be an if and only if condition. Like if there is a primitive root, then only it will like there will be like five and then there will be
Yes.
no. Okay.
Yeah. Yeah. I mean, I stated that suppose n has a primitive root. Yeah. Yeah. You need that assumption that there is at least one primitive root. Okay. So my next question is, when is a to the k a primitive root?
GCD of phi of n comma k is 1.
Let's just others think about it. I mean, you got the answer, right?
So
Yeah, it's fine. Let me know if there's any step which is not clear. We can go back. Note already that we're seeing one advantage of primitive roots to the question that was there before. We can simply write the set of all numbers co-prime to n simply with one single number, which is actually very convenient for analysis. Yeah. Yeah. So when is a to the k a primitive root? Simply when the order of a to the k is phi of n, right? By definition of a primitive root. So a to the k is a primitive root if and only if order of a to the k is phi of n, right? But we just said that this is the order. And so this is equivalent to saying that the GCD of phi of n and k is equal to 1, right? Yeah, is that clear?
Yeah.
Okay, great. And so how many such k exist? Note that we're only looking into this set where k varies from 0 to phi of n minus 1. Okay, so we're looking at this set k equal to 0, 1, 2 up to phi of n minus 1. We're asking how many of these k satisfy GCD of k comma phi of n equal to 1. Okay, so instead of phi of n, what if I wrote an m? Maybe that makes it clear. Have you seen this number before? It's called something.
am I allowed to say?
Let someone else answer. Yeah. So there's a function for this thing, right?
Phi m.
Yeah, exactly. Phi of m, right? Now that this 0 is the same as m if you're looking at mod m. So it's the same as the definition of phi, right? So this is literally phi of m. Yeah. So here m is equal to phi of n here. And so the answer
Wait, what's
is
m again?
phi of n, right? That this
Oh,
is the
so
same.
m is just phi of n.
Yes.
Okay.
Yeah, because we're looking at the set of k from 0. So that our k is the exponent, right? So our k is either 0 or 1 or 2 or so on up to phi of n minus 1. And we want that k to be co-prime to phi of n. So here m is exactly phi of n.
Yeah.
Yeah. So our answer is phi of phi of n. Yeah. Is this clear?
Yeah, that's cool.
Okay. Yeah. So yeah, the formula is kind of cool as well. And okay, so for what n is this odd, and for what, like, why is this even after, like, why is it even for most n?
Oh, can you repeat your question? My network got this.
Yeah, why
Can you
is phi?
repeat just what you said?
Yes, uh, so is this even for most n?
Yes.
Yeah, because it will be like the opposite for the inverse.
Yes, so that's more like a combinatorial argument. That's true. Uh, in fact, like, if a number and its inverse are equal, then we're saying that the number has order 2.
So
And
we
so,
need a number theoretic idea to prove that this will be even mostly.
well, I mean, you can do it directly as well, right? Well, I mean,
Yes.
phi of a number is always even if the number is at least 3. Right? It's the same idea basically. Uh, well, yes. I'll let you think about it. This is not so important actually,
Oh, why is it always even if it's at least 3?
because if x is co-prime to n, then so is n minus x.
Yes, makes sense.
Ah, but,
Yeah.
uh,
Or
but like if n is even, okay, yeah,
even then, it's the same thing. And
yeah,
the n by 2 cannot be co-prime to n, right?
yeah.
For n at least 3. Yeah. Okay. Okay, great. So we have this weird characterization. Okay. Let's try a problem. Yeah. Uh, Problem. Let's try. Okay. Yeah. Um, Here's a problem. Prove that. Okay. Let. Okay. So let's do it in steps actually. Uh, okay. Let let p be an odd prime. Okay. Prove that all factors of 2 to the p minus 1 are congruent to 1 mod 2p.
Hey, is it a Mersenne prime?
No, 2 to the p minus 1 may not be prime. Just p has to be an odd prime.
Okay.
Yeah. For Mersenne prime, you need 2 to the p minus 1 itself to be prime, right? But we're not imposing that condition.
What's a Mersenne prime?
Uh, so I think it's pronounced that way. I'm not sure. Yeah, a Mersenne prime is a prime uh, q such that q plus 1 is a power of 2.
Oh,
But yeah, that's not
With the we have to prove that all factors of 2 to the p minus 1 are congruent to 1 mod 2p.
2p. Yes.
But can't we multiply by some n and get that it is congruent to n mod p? Oh, sorry, factors. I thought multiples.
Yeah.
Really sorry. Really
Factor. Yeah, that's fine. Mersenne primes is sort of uh, looked into so much because most prime numbers that, like, if you've seen the news on mathematicians found the largest known prime yet, so most of them are Mersenne primes. Most primes that we keep finding the largest of are Mersenne primes. Of course, we know that there are larger primes, but explicitly those primes. Yeah,
oh
are
wait. So,
usually.
so is there like some sort of formula that generates Mersenne primes or something?
Oh well, I mean, there's no proper formula. Yeah, I mean, we don't know the pattern. I mean, we don't know exactly the pattern of exponents, but we do know that if 2 to the p minus 1 is a prime, then p itself must be prime, right? Do you see that? It might not be so obvious to see. So why okay, so why is 2 to the 21 minus 1 not a prime? For example.
Because it's divisible by 2 to the power 3 minus 1 and 2 to the power 7
Yeah,
minus 1.
yeah. So if you've seen this idea before, write it as 8 to the 7 minus 1, and then this will be a multiple of 8 minus 1, right, which is 7. So in general, if if p is composite, which is if you can write p as a times b for ab not equal to 1, then note that we'd have this. And so it cannot be prime unless p itself is prime. And so the point is that we can sort of, I don't know exactly how they do it, but the point is that we can iterate over smaller primes p and try to get a really large prime, which is like exponentially larger than p itself. So of course, not all primes work. It's not true that if p is any prime, then 2 to the p minus 1 is prime. But at least we only need to iterate over primes, and then maybe their patterns. Yeah, yeah. I don't know exactly what
Maybe
they
I
do.
have a generalization for this problem.
You have a solution to the question.
Generalization, not a solution.
Ah, okay. But oh, you're replacing 2 with n everywhere or something, or
No, 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 no. I have a generalization in the terms of p.
oh, what is the generalization?
Like p divides 2 to the p minus 1 and minus 1. So all the factors of 2 to the p minus 1 have to be divisible by p.
Wait, sorry. Could you say that once more?
Like we have 2 into 2 to the p minus 1 is congruent to 0 mod 2p.
Are you saying this? I mean, this is not true.
Multiplied by 2, the left hand side must be multiplied by 2.
Yeah. Yes. So basically this. Yeah.
Yes,
This.
yes, yes.
Yeah.
Wait,
This
I
is
proved
So,
it. Can I?
so when so we get
wait.
that 2 to the p minus 1 is divisible by the prime p, which
Yes,
makes sense
that's
by Fermat's last little theorem.
sure.
So now we proved that the factors are also divisible by p, then we are done.
Uh,
No, we just use formats little theorem
wait,
here.
wait. Sorry. What do you do after this? We
No, you
got
do
this.
formats, right? Because 2 and p are like co-prime to each other. So 2 to the power p minus 1 is 1 mod p.
Yeah, but he's trying to get to some other point. I just want to know what he's trying to do.
Like I want to prove that p divides all the factors of 2 to the p minus 1 minus 1.
But that's not true. That would mean that 2 to the p minus 1 is a power of p or something. Or, I mean, uh, I mean, 2 to the 7 minus 1 is 63, right? And the 3 divides it. But 7 doesn't divide 3, right? Like,
I'm telling a whole other thing, like the factor of 2 to the 7 minus 1 has to be divisible by p only.
why would the factors of this have to be divisible by p? That's what I'm saying. Like, 3 is a factor of 2 to the 7 minus 1
Like
minus 1, but it's not
CF.
divisible by 7, right? And this itself is divisible by p is automatic, but we can't say that all factors of this are divisible by p, right? Because that would mean that this is a power of p, which is not true. Unless I'm misunderstanding what you're trying to say. Okay.
Wait, can you give 5 more minutes? I think I can solve this.
Yeah, I'm waiting for a while. I'm just writing this step where suppose q is a factor. Okay, so first of all, note that okay, suffices to show that the prime factors of 2 to the p minus 1 are 1 mod 2p. Do you see why? So suppose I've shown that all prime factors of 2 to the p minus 1 are 1 mod 2p. Then do you see why all factors will be 1 mod 2p?
Yes.
Why?
Yeah, because other factors are just like products of the prime factors.
Yes, exactly. So any other factor is just a product of prime factor, maybe with multiplicity. But since all of them are 1 mod 2p, so the product will also be 1 mod 2p. Yeah. By the way, 1 mod p is also fine. 1 mod 2p is sort of obvious, but because it's also 1 mod 2. But okay. Yeah, let's just keep it
Then
one.
isn't it just
Right.
isn't it enough to just show that 2 to the power p minus 1 is 1 mod p?
No, because you can have a number which is 1 mod p, but then its factors are not 1 mod p, right? For example, 9 is 1 mod 4, but its factors are 3 and 3, which are both not 1 mod 4.
Oh, right.
Yeah, the converse is not true. Yeah. Okay, so just just another step. Suppose q is a prime factor of 2 to the p minus 1, q is prime. Then that's the same as writing 2 to the p is congruent to 1 mod q. Yeah.
Which means phi of q divides p.
Why?
Like 2 to the power 5 of q
Order
should
of
be
q,
Wait, sorry.
order of
Pranav.
a mod 2 mod q divides p. Like
oh,
that
yeah.
should be
Yeah.
there.
Yeah, but the order may not be the Euler-Quotient
Yeah.
function.
Yeah.
It can be anything.
Yeah.
We have odd q of 2 divides p, and so it must be p.
Yes. Good. Yeah, exactly. Yeah. Maybe let the others grasp that. Yeah.
What did you say?
No, don't repeat it. Okay, so re, do remember that. Okay, so let H be the order, right? So then just just tell me everything you know. Just write everything. What you know, what relations you know between H, P, Q, phi of Q, phi of P, phi of H. I don't know. Whatever. If H is the order of 2 mod Q, of course, that's what I mean. Then what do you know? What relations do you know by definition of order and all properties or questions you've done before?
Oh, h divides p.
Yes. So we know H divides P.
And
We
h
also
divides phi of q.
know H divides phi of Q. Because Q is definitely odd, right? So yes. And note this thing, right? You forget. So remember that P is an odd prime. So what are the factors of a prime?
One and itself.
Yeah. So what can H be?
P.
Oh, it can only be P.
1 or P, but why is it not 1?
Because 2 is not congruent to 1 mod q.
Yeah,
As
because
q
2
is
to the
greater than p.
2 to the 1 is not 1 mod Q. That's impossible. Because otherwise Q is a factor of 1, but Q is a
So
prime.
Q is just like any prime such that 2 to the power P is like 1 mod Q.
Yeah,
right?
because if taken Q, yes. Q is any factor of any prime factor of 2 to the P minus 1. In fact, I don't think I even need Q to be prime for this argument to go through.
Oh, okay.
Yeah. And so maybe I don't need this step, but it's fine. So the order
Don't you
is
need it?
P. Yeah.
I think you need it for the phi of q part, right?
Oh yeah, true. Yeah, I need it for the 5Q part. Yeah. Sure. Yeah. Q is prime. Okay, so yeah, so I know that phi of Q is Q minus 1. Okay, let's just keep it this way for now. Okay, so since the order is P, I now know that P divides phi of Q. But now here is where I use the fact that Q is prime, which means P divides Q minus 1. And so what is that in terms of mod P? Q is 1 mod P, right? And I already know Q is 1 mod 2. So then the 1 mod 2P thing is true. Is the argument clear?
Yes.
Okay.
Yeah.
Okay. But now there's a follow-up question not related to order. But yeah, I mean, it's kind of direct. Okay. Prove that there are infinitely many primes of the form two kp plus 1, where k is a natural number. P is the same prime P. Okay, I mean, okay. Uh, where P is an odd prime. So for example, There are infinitely many primes of the form 6k plus 1. There are infinitely many primes of the form 10k plus 1. Infinitely many of the form 14k plus 1, etc. Yeah, think about this.
Just considering 2 to the p minus 1. Wait, no.
Something like that, but yeah, a little different.
Can you scroll up a bit once?
Yes.
Is it the same P as before?
Yeah, I mean, it's just any odd prime p, right? It doesn't matter if it's the same or not. Yeah.
Okay, so all the prime factors of 2 to the power p minus 1 are of the form 2pk plus 1.
Sure. What next? Oh. Yeah, but what after that? I mean, does that give you infinitely many primes?
Let's just find it.
Wait, can I tell something?
Okay.
Like if 2 to the kp plus 1 is not a prime, it's one of the factors is prime.
Sure, but why does it give
And that
infinitely?
one factor has to be of the form 2 to 2kp plus 1.
Yeah, but why is it? Why does it give infinitely many primes of this form? I
Because we
for,
get that q minus 1 is divisible, like let any m be equal to 2kp plus 1. So we get that m minus 1 is divisible by 2kp.
no.
Why
Yeah, m
no?
minus one is divisible by 2kp. Yes, sure.
Yes. And which implies that m is congruent to 1 mod p.
Sure.
So there has to be one factor of m such that it is congruent 1 mod to it has to be congruent to 1 mod 2p.
Why?
Like you can put, but there also exists some inverses.
Yeah, I mean, yeah, that's not true. That same example, right? 9 is 1 mod 4, but 3 is 3 times 3, 3. Neither of the 3s are 1 mod 4. Take finite prime and then n is this product. Uh, yeah, but then the fact it this n may have factors which are not 1 mod 2p, right? So this n may have prime factors not 1. So the Eulers, I mean, was it Euler or Euclid? I forgot. Oh, yeah, I think it was Euclid, right? So yeah, Euclid's proof doesn't exactly extend
Yes,
because
that was Euclid's proof.
yeah, so it doesn't extend because you're skipping other primes. So then those other primes may divide n. So it's not a contradiction. Also, also this
Wait, I think we should involve the previous question in this one.
yes, exactly. Yeah. Also
So
this
we get
n
that 2 to the p minus. Uh, we can choose the prime factors of 2 to the p 2 to the p minus 2.
2 to the p minus 1, you mean?
Yes, 2 to the p minus 1. Yes.
Yeah, but these are only finite in number. So I mean,
Yes,
why
so
does it?
now we will prove that they are infinite.
How?
Like we consider there are finite of such types of primes. So we just like there let there be n such primes. We just multiply them to each other, which will be congruent to 1 mod 2k p plus 1.
Okay, 1 mod 2p. Yeah.
Yes.
Uh, Yeah, but what next?
Uh,
Oh, you're thinking about it. Yeah, sure.
Yes, I'm thinking.
Yeah, of course.
Is there somewhere by which we can prove 2 to the power kp minus 1 is congruent to 1 more 2p? The factors of it.
Can you try that? I mean, can you
No.
see if the arguments work?
Can you scroll up a bit once? I forgot the question.
Yes.
Okay. Okay, yeah. I think it would work like 2 to the power, all the factors of 2 to the power kp minus 1 are congruent to 1 mod 2p if k is a prime greater than p. I
Can
think
you say that once more?
all the factors of 2 to the power kp minus 1 are congruent to 1 mod 2p if k is a prime greater than p. I think.
Let me think about it.
Basically, see in this proof only,
Why? Because then h can be k.
but
Wait, I
h is
have
the
an
least
argument
number,
for
no?
that infinitude of such
Yeah,
factors.
yeah. Just 1 minute. No, but 2 to the p may not at all be 1 mod uh,
Ah,
q, right?
okay.
So yeah. Anurag, sorry. Go on.
Like then we can put we have the product of such n primes be equal to some large m.
Sure.
So we can put now some 2 to the m minus 1 uh, in the in mod 2p.
2 to the m minus 1. What did you do after that? Uh, hello. Did I lose audio?
No, he's on.
Okay. Yeah. Okay. He's thinking. Yeah. Sure.
Am I audible?
Yeah.
So we didn't denoted this product of primes as some large m,
Yes.
and we have that this m is divisible by 2p is congruent to 1 mod 2p.
Yes.
So we have that this is congruent to 2 to the phi some large factor of phi of p.
Sorry. What? So you said this. Just everyone else can just keep thinking. By the way. Yeah. So sorry. You said that this m is 1 mod 2p. What next?
This m is congruent to 1 mod 2p, so we get that this m is congruent to some large some 2 to the power large factor of phi of p.
What does that mean? Sorry, I don't get it. I'm
Like we
m
have
is congruent.
2 to the phi of p is congruent to 1 mod.
Yeah, I mean phi of p is just p minus 1. So uh, uh, is this what you mean? Can you write it in the chat actually what you mean in the next step? Maybe that will make it clear. You're not audible, by the way, if you're speaking. Okay, so the step. Okay, so if you've seen Euclid's proof, yeah.
Oh, can we consider 2 to the p to the k minus 1 for large k? We'll have,
Like this.
yeah, no, p to the k.
Oh. But then the problem is that this order can have like k distinct values.
Yeah, but then they're all divisible by p. So then p still has to divide the q minus 1.
Okay. And then q is 1 mod p, but why does that give us infinitely many?
Yeah, and then I think we can finish with LTE, but I think that's obviously bad.
Oh, I see. You're saying that if we repeat primes, then
Yeah, we can't repeat primes.
oh, it might work, but I don't want to get into the details because
Yeah,
it
obviously.
might get messy. Yeah, I'll think about it. It's a good approach. Yeah. It
Hey,
should.
hey, listen. Yeah. So there are infinitely many prime of the form of 2n plus 1, right? 2n plus 1.
With just odd primes, you mean?
Uh, no. Just to get from. Wait. Listen to me carefully. Suppose there are infinitely many prime of the form of 2n plus 1, and if we take n as a natural number, so and if we do prime factorization of n, so we get the p and k different. So there are infinitely many prime of 2kp plus 1.
Oh, this p is fixed. I mean, you can't change this p.
Oh,
I
but
mean,
that's still really cool, right? So all 2n plus 1 are primes. So like for any prime p, you can make k anything. Oh wait.
p
Oh
is
wait.
fixed. P, you can't change p. Yeah, so
Can you give a hint to my progress, like if my progress was in the right way or the wrong way?
yeah, let me think. So maybe this is confusing. So let p be a fixed prime. And so Aditya's idea was that you can just take any prime number, and then since it's like most prime numbers, like prime numbers other than 2 are odd, and then just look at primes greater than equal to 5, and then write them as 2n plus 1, and then just take out a prime factor of n and call it p. The problem is that this p changes as you change n, so you can't do that. I mean, this p is a fixed prime. So it's this p is pre-decided. Okay. Uh, yeah. So for the the idea. Okay. So Anurag started out with this saying this Euclid's idea for contradiction, and which was tried by someone in the chat as well. That okay. So suppose there are only finitely many such primes. Only finitely many such primes. Okay. Now all I need is to okay, so what was Euclid's proof of infinitude of primes? What did Euclid do? Euclid did was that Euclid took this, then just added one and said that note that all of these are co-prime to each of the QIs. But then but then what prime factor does this even have? Unless it itself is a prime. That's what we are trying to do here as well. Right. So I want to construct a number n such that 1, n and qi are co-prime for all I. And the
Can
second
I tell
point is
my
that,
idea for this construction?
yeah, just give me a minute. And
Like it should be some 2 to the power some p minus 1 congruent to 1 mod 2p, such that 2 to the that power of 2, so uh, that power of 2 minus 1 is co-prime to all such primes. Then we will have some new primes of the
yeah,
form
I mean, yeah,
2p 2kp plus 1.
yeah. So I need that all prime factors of n are 1 mod 2p. Do you see why this will suffice? I mean, uh, and let's just say n is more than 1 or something. That's clear. This will suffice because, I mean, in fact, even if you show that there exists a prime factor, there exists a prime factor of n, uh, that is 1 mod 2p, then we are done, right? Because then this prime factor is a new factor of this form 1 mod 2p, and it's different from all of the QIs. And so, yeah, we have a contradiction. So this is the sort of n that we want to construct. And so here's where we try to use the first problem, and that all factors of 2 to the p minus 1 are 1 mod 2p, and maybe we need to modify this slightly. So maybe some modification is needed here. So the idea is to try to modify 2 to the p minus 1 as in the expression to get the result. So think of how you modify it.
We can get it in the form of 2 to the m minus 1 instead of 2 to the p. Let m be the product of all the such finite primes.
Okay, and okay, so we take 2 to the n minus 1. I don't think it's even true that the that 2 to the m minus 1 has primes that are only 1 mod, factors only 1 mod 2p, right? So 2 to the p plus 1 over 3. Well, I mean, even if that works, that's still finitely many primes. So, but we still need infinitely many primes. But 2 to the p plus 1 over 3, I mean, it's a good idea because it's 1 mod p. But uh, um, yeah, but 2 to the 3 plus 1 over 3 is not 1 mod 3. It's 0 mod 3, right? Yeah. Okay. Yeah. Sorry. Yeah. You saying you're taking uh 2 to the q1 q2 up to qn minus 1. Do you want to look at this? Uh, yeah.
Like
I'm not.
q1, q2, n minus 1 will not be 1 mod p. We can like consider 2 to the qn, q2 till qn minus 1 mod 2p. Then it will be congruent to 1 mod 2p.
Are you saying this?
Yes, yes. Now we need to
Uh,
prove that this is all such q.
Sorry. Why is this 1 mod 2p?
Because that q1, q2, qn is congruent to 1 mod. Get that the power of 2 is congruent to 0, is congruent is congruent to 0 mod 2p,
Or
which
the power.
gives us that yes, which gives us that that will be congruent to 2 mod 2p. Thus 2
No,
minus 1 will be congruent to
no,
1 mod
no,
2p.
it doesn't give us 2 mod 2p. 2 to the power of 2 to the something that is a multiple of p is not 2
So
mod.
the q1, q2, qn will be a multiple of 2p, which is multiple of phi of p.
2p is not a multiple
No,
of phi
not
of p.
really phi of p, but it will be in some way that 2 to the some factor
I
of
mean, I mean, I mean, 2 to the 2p is 4 mod p, right? Not 2 mod p, for example.
yes, 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 not one.
Yeah. I mean, 2 to the kp is 2 to the k mod p. Yeah. To be able to deduce what this is mod p, you must look at the exponent mod p minus 1 actually. So looking at it mod p won't help. Yeah. So maybe not this. Yeah. So the okay. So this actually gives us a good idea because the point is that if you put this in the exponents, then if in exponents we must look at them qi's mod phi of p, but that's not relevant because our QIs are actually 1 mod 2p. So try to put these in, not in the exponent, but alongside 2. So maybe modify 2 and make it something. Change 2 to something else. So let's keep the p the same. So I'm trying to look at this, where this is something which is different from 2. So what can I put here?
The product of the prime.
Well, if I put product of the primes, then note that this entire thing is not uh, well, I mean it's not 1 mod p, right? It's 0 mod p. This is 0 mod p right now, right? But I want factors to be 1 mod 2p. So maybe not just the product of primes, something else alongside the product of primes. So what if I just put a 2, right? Yeah. And now let's focus on this number. What can we say about this? What can we say about the prime factors of this? Very similar to what we
we
did
can
here.
get that they are co-prime to all the such finite primes.
Yes, this step is already done, right? Because note that the GCD of 2q1, q2 up to qn power p minus 1 and qi is exactly 1 because this is a multiple of qi and so we have a minus 1. So the first condition is already satisfied. What can we say about the second condition? Can we say something as strong as this by
No,
this
because h
argument?
equals 1 comes back.
Yeah, exactly. Yeah. The point is okay. So 2 to qn to the p minus 1 and very similar to what we did before. Suppose I have a prime factor r is a prime factor. It's exactly the argument that I did before. And so suppose r is a prime factor of this thing. Yeah. Then what are we saying? We're saying that q2 q1 q2 up to qn to the p is congruent to 1 mod r. And then what does this mean? If the order is h, then h divides p, which means h is either 1 or p. H cannot be 1 because this 2q1 q2 up to qn. But okay, so let's see. Yeah, so what happens if h is 1?
H can't be
Then
one like for the then uh, because 2 to a Q1 Q2 Qn will be one mod 2 mod,
this is what we need for h. Yeah, what happens in this case?
but it can't be.
Why?
Wait, R is also prime, right?
Yes.
Yeah, so then, oh, wait.
Okay, what happens in this case? Let's resolve this first. In this case, since we also know that h divides r minus 1 because h divides phi of r, then this would mean p divides r minus 1. And so r is 1 mod p, and
Wait, how R minus 1?
because that's phi of r, right?
Oh, yeah.
I know that the order divides phi of the mod,
Yeah.
right? And so h divides phi of r, and so r is 1 mod p, but that also means r is 1 mod 2p because r is odd, which is a contradiction. This is a contradiction because r is different from each of the qi's, but it's also 1 mod 2p. But we already said that the list of 1 mod 2p primes is this. So yeah, so this is a contradiction. So we're only left with this case where h is 1. Yeah, think about this now.
So H has to be 1.
Yes, otherwise we have a contradiction. Yeah. So what is this really saying? So basically we started from
Then
this.
it is saying that some multiple of R is of the form 2 no, 2 kp no, like plus 1.
Minus 1, you mean? Uh,
It will be plus 1, I guess, because
oh,
2
plus 1.
Q1
Yes.
to 2 Qn is 1 is 2. Yes.
Yes. Yes. But notice we're saying some things of this form. If r is a prime factor, well, let this 2q1 q2 up to qn thing be m, right? Then we're saying that if r divides m to the p minus 1, then r also divides m minus 1. That's sort of strong, right? I mean, the opposite is definitely true, but we're saying that this direction is true as well. So that's a little weird. So yeah.
Okay, so we're trying to prove that there are some primes that aren't, not just
Yes.
none.
Yeah,
Okay.
we just need to show that there is one such r for which this does not hold true, right? Is that clear? I mean, we just need to show that there is one such r for which this is not true. Okay, so think about this. So how will you find a prime which prime factor of 4 to the 7 minus 1, or maybe 9 to this? Okay, so how will you find a prime factor of uh, sorry, I'm just trying to find some good example. 14 cube minus 1, which is not a prime factor of 14 minus 1. This is all I need for a contradiction. How do I find such an R? Like, what would your first intuition be? Okay, maybe let's change this to square. What's your first intuition in order to find such an R? There is such an R, right? Can you tell me what such an R is?
3 or 5.
Yeah. So the point is that,
Just 5.
yeah,
3 or 5, 3 or 5. Yeah.
yeah, we can just factorize this and then just look at prime factors of this. Yeah. And hope that they're not the same as prime factors of 14 minus 1.
No, for a cube minus b cube, it's a minus b into a square plus ab plus b squared, right?
Yeah, exactly. So if I'm trying to find a prime factor of 14 cube minus 1, which is not 14 minus 1, it suffices to find a prime factor of this. Yeah. And then whatever this is.
No,
This is,
that's 211.
yes. Yeah. And 211 is prime. Yeah. Yeah. 211 is prime. Yeah. So yeah, just 211. Yeah. So can you do something similar here? So all I need is to find an R for which this is true but this is false, so that I have a contradiction. For a contradiction, I need this. So how do you find such an R? Exactly the same method as we did right now. Like, what do we do?
You just choose R dividing 1 plus m up to the m to the p minus 1, and then
Exactly. Yeah. Just choose any prime R dividing the ratio of this, right? So note that m to the p minus 1 factorizes, right? As m minus 1 times m to the p minus 1 plus m to the p minus 2 plus so on up to 1. So let's choose any prime dividing this. Literally any prime. What happens if R also divides? Okay, what? Okay, so the question is, can R divide m minus 1?
no, because then R divides p as well, just by modular.
Exactly. Yeah. The problem is that if this happens, then m is congruent to 1 mod R. Yeah. But then this is congruent to 1 to the p minus 1 plus 1 to the p minus 2 plus so on up to 1 mod R, which is congruent to p mod R. Yeah. So let me just write this again. So I'm saying that if R divides m minus 1 and R divides m to the p minus 1 plus so on up to 1, then note that note that by this divisibility, 0 is congruent to m to the p minus 1 plus m to the p minus 2 plus up to 1. But from this, each of this is just 1 plus 1 plus up to 1, or more, 0. But this is p mod R, which means R divides p. But can R divide p? R is a factor of this thing. What is this mod p? I mean, if R divides p, then R is equal to p, right? Because R and p are primes. But does p divide this thing? No, because this is 1 mod p. So P cannot divide this, right? Is this clear? So we've actually arrived at a contradiction in this case as well. So this is a contradiction. But P does not divide M to the P minus 1. Contradiction. And so we've arrived at a contradiction in every case. And yeah, done. Which means
Oh, right. Yeah, that makes lots of sense.
yeah. So yeah, I'll just go over the proof. So the so this okay, so this idea also comes up a lot of times, this sort of order business, and especially if you have a prime number here, then often you can just sort of directly deduce the order. So anytime you see 2 to the, I mean, a to the b is 1 mod c, you immediately know that the order is a factor of b. Yeah. Also a factor of phi of c. So yeah, so a to the b congruent to 1 mod c means that order is a factor of b, order is a factor of phi of c. Yeah. And yeah, so we did this problem, and then to do this problem we just had to sort of modify the construction in the previous problem and do the math. Yeah. So yeah, I mean, one hint as to why taking this in the exponent was is, well, I mean, it seems tempting at first, but the 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 reason why it doesn't work is that because once you look at exponents, then you're working mod phi of p, not mod p. So it's not like 2 to the a plus p and 2 to the a are the same thing, mod p. So this is not true, right? And so it's to the a plus p minus 1 is 2 to the a mod p. And so since these qi are 1 mod p, so you should put them alongside this. And so this construction just works out. Yeah. Okay. I think we are way out of time, and I think I think I have a good set of problems from various books that I can just make a correction of. Questions?
Hey, Alan, recording.
Yeah, you can end the recording. Yeah, thanks.